Okay, let's talk about vectors for the GCSE higher tier math paper. Do they feel a bit tricky? Yeah? You're not alone. But honestly, in this quick explainer, we're going to break them right down. We'll go through everything you need from the G24 and G25 specifications, starting with the absolute basics and building all the way up to those geometric proofs that always seem to pop up. So let's get you feeling confident for that exam. Let's start with a really simple idea. Imagine I told you to just walk 5 miles. That's not very helpful, is it? You'd have no idea where to go. But what if I said walk 5 miles north? Now you've got a clear instruction. That little combo of distance and direction, well, that's the whole idea behind a vector. It really is that simple. So that brings us to the big question. What is a vector really? Well, in maths, we need a super precise way to talk about a journey, one that has both a length and a specific direction. And you guessed it, that's exactly where vectors come into play. Right, here's the official definition you'll see in textbooks. A vector has 2 key parts. First, magnitude, which is just a fancy maths word for its size or its length. And second, direction. So it's way more than just a number. It's a number with a mission, a number that knows where it's going. This slide really nails the difference between a vector and something called a scalar. A scalar is just a plain old number, like speed. If I say I'm going 50 miles per hour, that tells you how fast, but not where. A vector, like velocity, gives you the whole story. 50 miles per hour north. It's the complete picture. So in your exam, you're going to be writing vectors like this, as column vectors. This is a huge part of that G24 topic on translations. It's really just a set of coordinates for a journey. The top number tells you your x-axis movement, so positive for right, negative for left, and the bottom number is your y-axis movement, positive for up, negative for down. It's such a neat and tidy way to write down a journey. All right, so now that we know what a vector is and how to write it, let's get into the toolkit. What can we actually do with them? This is the heart of topic G25, and you'll be happy to hear the maths is surprisingly simple. Think about adding vectors, like going on 2 journeys, one after the other. To figure out the single journey that gets you from the start to the final destination, you just combine the movements. It's as easy as adding the top numbers, the x parts, together, and then adding the bottom numbers, the y parts, together. And guess what? Subtraction works in exactly the same common sense way. Now, what about multiplying a vector by a normal number, a scalar? Well, all that does is change its size. So if you multiply a vector by, say, 2, you're just making the journey twice as long, but keeping it in the exact same direction. And to do it, you just multiply both the top and the bottom numbers of the vector by that scalar. Simple as that. Okay, and this is the golden rule, the absolute key for those tougher questions. Pay attention to this one. If you can show that one vector is just a scaled up or scaled down version of another one, meaning you can get from one to the other just by multiplying by a scalar, then they are parallel. You have to burn this rule into your brain because it is everything when it comes to vector proofs. Right, let's move on. We've got these skills with numbers, so how do we actually apply them to solve problems with shapes and coordinates? This is where it starts to get really useful. You see this formula, you absolutely 100% must know this. To find the vector that describes the journey from point A to point B, you subtract the position vector of A from the position vector of B. Now, a position vector is just the journey from the origin, from 0, 0, to that point. So an easy way to remember it is it's the destination minus the start. This formula is a total game changer for geometry problems, I promise. And now for the main event. This is a massive part of the G25 specification. Geometric proofs. This is where we pull every single skill we've just talked about together to prove things about shapes. It's a classic higher tier question, so let's make sure we nail it. So here we go, a classic exam problem. You're given 4 points, and you're asked to prove that the line connecting A and B is parallel to the line connecting C and D. Now, it might look a bit intimidating at first, but trust me, if we just follow a clear strategy, it's totally manageable. The most important thing here is to have a clear game plan and not to panic. So, step 1, we use our destination minus start formula to find the vector for the journey AB. Step 2, we do the exact same thing to find the vector for the journey CD. Once we have those 2 vectors, we can move to the final step, comparing them. And this is it, the aha moment. If you look at your 2 vectors and you can see that vector AB is just a multiple of vector CD, like maybe AB is just 2 times CD, Then you've done it. You've proven they are parallel. You've just used our golden rule to build a logical proof. It's an awesome feeling when it all clicks together like that. So let's do a super quick recap of the essentials. 1. Vectors are journeys with both size and direction. 2. The basic arithmetic, adding, subtracting, multiplying, is really straightforward. 3. Your secret weapon for finding vectors between points is that b minus a formula. And 4. The golden rule for proofs is to show that one vector is just a scalar multiple of the other. That's the core of it. Okay, to finish up, I'm going to leave you with a little challenge. We know how to prove that two lines are parallel. So, how would you adopt that to prove that 3 points, let's call them A, B, and C, are collinear, which just means they all lie on the same straight line? Here's a hint. You need to show that the journey from A to B is parallel to the journey from B to C, and think about what that common point B means. Have a go at structuring that proof. Thanks for joining me for this explainer.